L'effet Doppler-Fizeau est
The
l'un des outils
Doppler-Fizeau is one of the most invaluable tools in astrophysics. It allows a direct measurement of the velocity of stellar objects, and so enables the study of their movement. When used along with the viral theorem or the Kepler's laws, both bringing in the velocities, it also allows indirect measurement of the masses of celestial bodies. It concerns the effect of the combination of velocities when a source moves with respect to the observer. The wavelength of the emitted wave, it may be sound or light, decreases if the source moves towards the observer, and thus we observe blue shift. The wavelength increases if the source moves away from the observer. In this case, red shift is observed. One can see here a moving light source and a representation of the perception of wavelength by the observer. When the source moves forward, the wavelength is compressed, and the light seen by the observer is bluer. While moving in the opposite direction, the wavelength increases, and so it is seen redder. Redshift is observed. How does the Doppler effect work? Considering at first a source at rest, it was just said that the Doppler effect is due to the combination of movements, the combination of velocities, so the velocity of wavelength propagation and the velocity of the emitting source. Here we have a source at rest emitting a spherical wave with some speed, c, and wavelength lambda 0. Lambda 0 is shown here. So wavelength is the pulsation of the wave. In the case of light, the velocity is equal to c. Now, what is happening when the source moves? Here we have a wavefront that was emitted at the time when the source was in this place. The source will continue to emit the wavefronts while moving forward. While this wavefront was emitted, this one was propagating, and so on. Here, we arrive at a situation in which the wavefronts were emitted in the same way as when the source was at rest, but are combined with the velocity of the source. It can be noticed that the wavefronts are closer to each other toward the observer, and further from each other in the opposite direction. How does it work? Here, the wavelengths will appear bluer, and here redder. Now, let's draw the axis representing the direction of the observer, and the source with some velocity, v. Then, the source emits the wavefronts, so we can draw one here and another one here. Wavelength emitted by the source at rest will be called lambda 0. Now we consider delta t, the time interval between two wavefronts seen by the observer. What will be this interval? Obviously, if the source is at rest, delta t is equal to delta t0, which is also the period of the wave. We can say that delta t0 is the period of the wave, the period of the wave at rest. The relation between those two time intervals is delta t equals delta t0 if nothing moves. But if the source is not at rest during the time delta t0, it will move at a given distance, delta x, continuously emitting wavefronts. Finally, the time separating the wavefronts seen by the observer will be equal to delta t0 minus another time interval that is equal to the time needed for the source to move with the velocity v, a distance delta x that is shown here. Of course, the velocity of the wave is c. Now, one just has to rewrite delta x as v delta t0, which is the distance the source moved during the time that separates two wavefronts at rest with the velocity v. Obviously, it is divided by c, as the wave is propagating with the speed of light in the case of the electromagnetic waves. We also see that lambda equals c delta t. So it suffices to divide the whole expression by c to obtain that lambda, the wavelength seen by the observer, is lambda minus v divided by c, lambda 0. This is the expression for the Doppler effect that combines the wavelength in the reference frame of the source. So what the source sees while emitting the waves and the wavelength seen by the observer. Here the case of the source moving toward the observer was presented. But if the source moves away, the sign changes here for plus. So we would be in the situation where the wave propagates in a direction opposite to the observer. The expression for Doppler effect can be written in several different ways. In the previous slide, it was written in this way. The minus sign is due to the fact that, as was seen in the figure which was just drawn, the source moves towards the observer. The plus sign appears if the source moves away from the observer. It should be noted that the sources do not always move in the same direction as the line of sight to the observer. Let's say the observer is in this place. In one situation, the source can go in the direction of the observer. But there can also be in a case in which the source moves in the other direction. Let this be the velocity vector. The angle theta is the angle between the line connecting the source with the observer and the velocity vector. What counts in this case is the velocity of the source along the line of sight, the velocity that is projected on the line of sight. So in fact, the full expression for the Doppler effect is delta lambda, or lambda minus lambda 0 divided by lambda 0 equals minus v over c times the cosine of the angle between the velocity vector and the line of sight connecting the source to the observer. Clearly, theta takes the value in the range from 0 to pi. The redshift is often written as z. And relates, for example, to the cosmological redshift. The expression for the Doppler effect can be written in a more compact way as lambda equals lambda 0 times 1 plus z. If the velocity or the redshift of the source is known, one can relate the observed wavelengths to the wavelengths emitted by the source, as if it was at rest. We have already defined the redshift, but how in practice is the redshift measured, or the blue shift is measured? Speaking of colors, one can see here an example of the spectrum, the image of a star, as seen with a telescope. The image, instead of being directly recorded with the CCD camera or another detector, is divided into many parts from which one is selected. In fact, in focal plane of the telescope, a mask is placed in the shape of the slit, as shown here. The image, if the slit can be observed with a prism or a diffraction grating. In this way, the image of the slit can be observed over the whole range of wavelengths. So the spectrograph works in such a way that the image is formed in the focal plane of the telescope. Then a part of this image is selected. Here the star is seen as a point, so the light is dispersed from the blue to the red part of the spectrum, as illustrated in the figure. If the observed object was an external light source, there would be a spectrum like this one at all points of the slit. So what the spectrograph does is to create an image of the slit at all wavelengths. Here, we would have the slit seen in green light. And in this place, the image of the slit can be drawn at the wavelengths towards the red part of the spectrum. The idea behind this is to create the image of the slit at all wavelengths. The slit is placed here. The image of the slit is created. The spectrum is the combination of the successive images of the slit. Once we have the spectrum, how can the redshift be measured in practice? As an example, we show a nebula, or a gas cloud, emitting emission lines. This gas cloud moves, for example, in the direction of the observer that is placed here. In this situation, the cloud has some velocity towards the line of sight to the observer. Let it be the velocity, v. In this case, a blue shift is expected to occur. Let's draw the spectrum of this object. We place two axes. and draw a simple spectrum that is just an emission line. On the y-axis, we have the flux, F lambda, and the x-axis corresponds to the wavelength. If we consider this simple spectrum composed of one emission line, for example, the hydrogen line, H alpha, at 6,565 angstroms, what will happen to this line? In this case, we have a blue shift. So the line shifted towards the blue will be seen here. And in this case, the wavelength of the line will be lambda equals lambda 0 times 1 minus v divided by c. Conversely, if the velocity vector is in the opposite direction, so when the source moves away from the observer, then we observe a redshift, and the spectrum shifts towards red, and will be seen in this way. The redshifted line will have the wavelength of lambda equals lambda 0 times 1 plus v divided by c. So in this case, the cloud moves towards the observer. If the cloud moves in a different direction than along the line of sight to the observer, we can choose, for example, this direction. One has to multiply the velocity, v, by the cosine of the angle, theta. We have just seen an example of a cloud emitting a line, in our case, the line H alpha. Now, we can look at the situation in which there is an absorption line. Obviously, Doppler effect applies also in this case. Here we have a star, whose spectrum is that of the black body. The light of the star passes through the cloud composed of cold gas and propagates towards the observer. The cloud of cold gas contains atoms, for example, hydrogen, but it can also include other atoms. We can have, for example, the line H alpha that we have just seen, with the wavelength 6,560 angstrom. So the optical line, or the line of Lyman series, Lyman alpha, at 1,216 angstrom. We have the situation in which there is a cloud of cold gas that absorbs light, creating an absorption spectrum, seen superposed with the spectrum of the star. Firstly, we draw the velocity vector of the cloud. And the spectrum. As before, the y-axis corresponds to f lambda, x-axis to lambda. We can also have fv, v, if we would like to present the spectrum in a different way. This is the curve representing the black body spectrum, the Planck spectrum. As an example, it could be the spectrum of the Sun at 5,780 Kelvin. What will be observed depends on the velocity of the cloud. If the cloud is at rest, an absorption line, for example, the line H alpha, will be observed at lambda equal to lambda 0 equals 6,565 angstrom, as v equals 0. If the cloud moves towards the observer, the line will be blue shifted, and the same absorption line will be observed, but toward the blue part of the spectrum. In this case, lambda equals lambda 0, 1 minus v divided by c. As we have seen, the Doppler effect applies for the emission lines as well as for the absorption lines. Now we will see in details how the Doppler effect can be used. As an example, we take the case of the rotation of the Sun or of the stars in general. We draw the rotation axis of the Sun and the solar equator. Then we can take the solar spectrum by placing the slit in this way, in order to select a piece of the Sun. Here, the slit is drawn quite large on purpose. In this position, at the border of the Sun, the velocity vector is directed towards the observer. It will be at position 1, on the equator. The velocity vector is tangential. This will be position 3. In this place, the velocity vector has the opposite direction than at position 1. It can be called position 2. It was said that the spectrum is the image of the slit at different wavelengths. We will represent it in this image, drawing the slit, thicker than before, and selecting a line that would be in the green part of the spectrum. Then we will look at the points 1, 2, and 3 on the slit. The point 3 is in this place, the point 1 in the upper part, and the point 2 is here. We can see that the point 2 is moving away from us, so that the point that is in this place will be redshifted. The velocity at point 3 does not have a radial component, so this point stays in the same place, its wavelength being equal to lambda equals lambda 0. Point 1 is moving in our direction, so it will be blue shifted. One can imagine the series of points for which the redshift will be measured. There are different velocities, so in this place the points are blue shifted. In this way, a new image of the slit can be seen when all the points are shifted in such manner. If the wavelength at rest is equal to lambda 0, once shifted, all the wavelengths lambda 0 will be placed on the new image of the slit. Consequently, all the emission or absorption lines of the sun will be seen inclined in the spectrum. Obviously, if the star was rotating in the other direction, the new image of the slit will be tilted, also in the opposite direction. Now, let's look at an important application in astrophysics, namely the search of the exoplanets using the measurement of the radial velocities of the stars that host a planetary system outside the solar system. It is not an easy task, because the distance between a star and a planet is small, and the luminosity contrast between those two is generally very high. The contrast can reach tens of magnitude, in some cases even more, so it is difficult to directly detect an exoplanet with direct imaging around the whole star. Let's see what happens when the planet rotates about the center of mass of the star-planet system. Representing a few positions during the planet's rotation and drawing what is happening at each position. Here is the star and its planet are at position 1. In this place, we mark the center of gravity of those two objects. Here, position 2 of the star and the corresponding position of the planet. At position 3 of the planet is here, while for position 4, here. Of course, each time the velocity vector at positions 1, 2, 3, and 4 is equal to Vmax, one has to pay attention to the fact that the velocity is equal to Vmax times sinus, which is measurable with spectroscopic measurements on account of the inclination of the planetary's orbit with regard to the plane of the sky. This is the direction to the observer. When the spectrum of the system is available, it is only the star that is visible, and not the planet. Those are the oscillations of the star's velocity that will be detected around the center of mass of the star-planet system. Let's draw this situation. The important data that can be obtained from the star's spectra, taken at regular intervals. The velocity will be presented on the y-axis, so v sine I as a function of time. This curve is called the velocity curve. Obviously, the stars in the galaxy have some velocity, so we need to center the axis on the mean velocity of our stars in the galaxy. This velocity is typically equal to some tens or hundreds of kilometers per second. The mean velocity can be represented in this way, with an arbitrary direction. This vector represents the mean velocity of a star in a galaxy, so the velocity of the center of mass of the system. The star rotates about the center of mass, and we can put the data coming from the different positions on the diagram. Starting with position 1. If the observer is here, there is no radial component of the velocity, and no change observed with respect to mean velocity. On the contrary, for position 2, the velocity vector is radial with respect to the observer, and a point corresponding to this position can be placed here. This velocity is equal to v mean plus v max sine I. Position 3 corresponds to position 1, with the difference that this point is obtained further in time. As before, the velocity is equal to the mean velocity because of the lack of radial component. Position 4 is similar to position 2, but the velocity vector has the opposite direction. So on the diagram, the point should be placed on the other side. The velocity in this case is equal to v mean minus v max times the sine of the inclination. By connecting the points, we obtain the velocity curve, which is obviously periodic. So what can be measured directly is the rotation period of the star around the center of gravity, which is equal to the rotation period of the planet around the center of gravity, as we are in the frame of the center of mass of the system. That kind of curve, the velocity curve of a star, suffices to deduce the period of rotation of the planet and the maximal velocity of the star rotating around the gravity center. This was another important application of the Doppler effect. At last, the Hubble law. So we do now a drastic change in spatial scales and enter into the domain of cosmology. As the universe expands, the distances between galaxies, schematically presented in the figure, will increase with time because of this expansion. So, after some time, the galaxies have moved away from each other. The metric expanded, and all the arrows drawn here on the image become larger. Due to the increased distances, if the observer was placed in one of those galaxies, he or she would observe the other galaxies moving away. The Hubble law relates the velocity of galaxies that move away, this velocity being completely radial with respect to the line of sight to each galaxy. So the velocity of these galaxies is proportional to the distance between the galaxies. These velocities of the galaxies are measured using the Doppler effect. The distance, as it will be seen later, is measured with the distance modulus. Then, the proportionality constant can be deduced. As we have seen during this lecture, the Doppler-Fizeau effect has lots of applications in astrophysics, from the search for exoplanets using velocity curves of stars hosting planets, to the rotation of stars, and to the measurement of the temperature of the interstellar medium, or to the measure of the rate of expansion of the universe using the recessional velocities of galaxies. We will get back many times to the Doppler effect during this course. It is worth mentioning that each time a theoretical model, an idea, or a concept predicts velocities, the practical way of measuring them will be by using the Doppler effect.